Today we are diving deep into something you're doing right now without even thinking about it. We're going to unravel the absolutely incredible science of breathing.
Think about it. You take more than 17,000 breaths every single day. It's the automatic rhythm of your life. But what's actually going on with each one? What is this hidden, high-stakes drama that powers every single one of your cells?
Because, breathing isn't just about puffing air in and out. It's a constant, vital conversation between your body and the atmosphere around you. A life-or-death exchange happening molecule by molecule.
To really get how life evolved to breathe, we have to start with the non-negotiable rules of the game, the laws of physics. Because no matter how clever biology gets, it always has to obey the basic principles of chemistry and physics.
And rule number one, the most important one, is all about something called partial pressure. The easiest way to think about it is that gases are, they're kind of lazy. They will always move from an area where there's a lot of them, a high partial pressure, to an area where there are fewer of them. It's just like a ball rolling downhill. It happens automatically, no energy needed. This one simple idea drives literally everything else.
Now, this might sound complicated, fixed law of diffusion, but don't worry. It really just boils down to 3 simple design rules for any breathing system. If you want gas to move fast, you need 3 things. 1, a gigantic surface area. 2, a super thin barrier for the gas to cross. And 3, you need to keep that downhill pressure difference as big and steep as possible. Every single respiratory system we're about to look at is just nature's solution to these 3 challenges.
And check this out. This table shows that pressure difference in action right inside your own body. Just follow the numbers for oxygen, O2. It starts out in the air at a high pressure of 159. By the time it's deep in your lungs, it's at 104. And in your blood, waiting for a refill, it's way down at 40. See? That's the downhill path that just pushes oxygen into your body. And CO2 does the exact same thing, but in reverse. It goes from a high of 45 in your tissues to a low of 40 in your lungs, so it can just flow right out.
Okay, so with those physical rules in mind, let's take a look at the wild and ingenious ways that life has evolved to solve this whole breathing problem.
For tiny critters like flatworms, just being thin is enough. Gases can move directly in and out. Earthworms basically breathe through their skin. But as animals got bigger and more complex, they needed specialized gear. You've got insects with their own personal network of air tubes, fish with their incredible gills, and of course, the lungs that we're all familiar with.
Now, we have to talk about fish gills because they are a masterpiece of engineering. Their secret is something called countercurrent exchange. Just imagine water flowing one way and the blood inside the gill flowing the opposite way. This setup means the blood is constantly meeting water that's a little bit richer in oxygen. The result? That pressure difference, that downhill slope, stays steep across the entire gill, pulling oxygen in the whole way.
And this clever design makes gills unbelievably good at their job. I mean, air has tons of oxygen, but water has very little. So to survive, fish had to evolve what is, hands down, the most efficient breathing system on Earth, yanking over 80% of the available oxygen out of the water. Just incredible.
Birds also have a completely wild system because flight takes a ridiculous amount of energy. They use a whole system of air sacs to create a continuous one-way flow of fresh air across their lungs. So unlike us, they never mix fresh air with old, stale air. They're literally exchanging gas when they breathe in and when they breathe out. It's a game-changing adaptation, especially for flying at high altitudes.
Okay, so after looking at nature's superstars, the fish and the birds, let's finally turn the focus inward and see how the human machine pulls this off.
Our system is really just a big branching tree. Air comes in, goes down the main trunk, the trachea, and then splits into smaller and smaller branches, the bronchi and bronchioles. And it all ends in these tiny little clusters of air sacs, like leaves on the tree, called the alveoli. This is where the magic really happens.
And the engine that drives this whole thing is the diaphragm. It's this big, powerful muscle right at the base of your chest. When it contracts and pulls down, it makes your chest bigger, the pressure inside drops, and air rushes in. That's a breath in. Breathing out is usually pretty lazy. The diaphragm just relaxes, your chest gets smaller, and air gets pushed out. It's that simple mechanical rhythm. Diaphragm down, air in. Diaphragm up, air out.
So, remember rule number 1 from Fick's law? Maximize surface area. Well, our lungs are masters at this. If you could somehow take all 300 million of your tiny alveoli and lay them out flat, they would cover about 75 square meters. That's roughly half a tennis court, all folded up neatly inside your chest.
But here's a little twist, something you might not expect. For all their amazing complexity, our lungs are actually, well, kind of inefficient compared to a bird's or a fish's. Why? Because we use what's called tidal breathing. We breathe in and out using the same tubes. That means fresh air is always mixing with old, leftover air. We can never get a completely fresh lungful of air in one go.
So let's zoom in, way in. Let's follow the journey of a single molecule of oxygen as it makes that critical leap from the air you just breathed into one of your cells.
This gets us back to Fick's second rule, minimize the distance. And boy, does our body take that seriously. The barrier between the air in your lungs and the blood in your tiniest capillaries is almost nothing. It's just 3 microscopic layers. It is an unbelievably short trip, which allows for that lightning-fast diffusion that keeps you alive from second to second.
Now, once oxygen gets into the blood, it doesn't just swim around on its own. It gets a VIP escort. It grabs onto a protein in your red blood cells called hemoglobin. And the real genius of hemoglobin is that it's a shapeshifter. In your lungs, where there's tons of oxygen, it holds on tight. But out in your tissues, where oxygen is scarce, its grip loosens and it drops off its precious cargo right where it's needed most.
The return trip for the waste product, carbon dioxide, is a little more complicated. Some of it just dissolves in the blood, and some of it hitches a ride on hemoglobin. But the vast majority, we're talking 70%, gets converted into something else entirely, bicarbonate ions. This is a super clever chemical trick that not only lets us carry a ton of CO2 out of the body, but it also doubles as a buffer to keep our blood chemistry perfectly balanced.
Okay, so we've got this incredibly elegant, multi-step process happening all the time. But what's in charge? Who's the unseen conductor making sure this rhythm never ever stops?
You'd probably think the main reason you feel the need to take a breath is your body screaming, "I'm running out of oxygen," right? It seems like the most logical answer, but is it the truth? Here's the big reveal, and it's a shocker for most people. Your brain isn't really paying that much attention to your oxygen levels. Instead, its main job is to monitor the buildup of carbon dioxide in your blood. When CO2 levels start to rise, that's what sends the powerful, undeniable urge to your body, breathe now. The need for oxygen is actually a pretty minor player in all of this. So, in the end, every single breath is this beautiful testament to evolution solving the fundamental puzzles of physics. It's a physical, chemical link to the entire world around you. It reminds us that we are profoundly, intimately connected to our environment with every single rise and fall of our chest. What does that connection really mean to you?